And we're going to use this word superimposable. So superimposable means that one of them can fit exactly on top of the other or in place of the other. It's sort of a more specific way of saying they're the same. Because the same could technically mean like literally the same thing. And if you have two things, you have two things. So to say they're superimposable just means they're basically the same. So if we look at the two things that you made, they should be superimposable, meaning if you line them right up, they correlate exactly one-to-one. They're the same. Does everybody see that in your own models? That they're superimposable? Yeah, like you kind of get them really close and you can see that they exactly correlate everywhere. Yeah. Okay. So now we're going to add things to them and keep asking ourselves if they are still superimposable or not. So everybody take one of the little tiny round ones that you said were hydrogen. Oh, you got it, thank you. And put one on each molecule. Okay. If you put one on each, are they still superimposable? Yes. Still superimposable? Yes, right? Because they still, you can still line them up so that everything lines up exactly with one another. Okay, now let's take a red one and put a red one on each molecule. Does everybody have at least two red ones? No. All right, we need some red ones. There's some in here. You just need one for each. You need red? How many do you need? Yeah, one. One more? So many. Who else is missing red? I don't have any red. Oh, okay. Sorry, yeah, these are, I forgot. Here, use the different textured ones so you can see it better. So like, there's these, so that you can tell that they're the same or different. So that you're missing the color. You need more red here? I only have some more. You guys ready? Just one? All right, let's see if we can find one more. All right, if you put the two reds on there or whatever ones you found, are they still superimposable? Right? They are. Okay, so here comes something different. Put the two, no, not exactly, line them up, okay, so that they are mirror images of each other. So if there were a mirror in the middle, it was like one is looking into the mirror and looking at the other one. So like the little ball and the big ball are matching like this, the other two are like up and down. Yeah. Everybody got that? Okay. Everybody got your mirror images? It's like they're looking in the mirror at each other? Good. There you go. Okay. All right, so now you need two more pairs of colored pieces. Now you can use, actually, let's just use one more. Let's just take one more. So you can use blue, you can use light blue, you can use gray, green, whatever you've got. One more pair that's different from the other two, that you've already, from the other ones you've already put on there. And put one on the top of each molecule that you made. All right, and they're still kind of looking in the mirror, right? You guys know what looks like that? Okay. So, question then is, are these two superimposable? They are. Try it. Try to superimpose them, get them all to line up. It doesn't quite work, right? So they're not superimposable. You can get two of them to line up, but then the other two are switched. See that? No matter how you turn it, you can get two of them to line up, and the other two are not lined up. So that actually makes these two different. Non-superimposable. Even though they're connected in all the same ways, it's a carbon, let's say, in the middle, with the same pieces connected to each one, they are actually different molecules. And the name for that is, in general, stereoisomers. There's a more specific name, enantiomers, but we're going to focus on stereoisomers for now. So let's draw this, and let's draw how we would do this in 3 dimensions, or in 2 dimensions. So go back to what we did a few weeks ago when we looked at the structure, the tetrahedral structure of carbon. We used that dash and wedge notation to indicate that one's coming out, one's going back. We just kind of said, okay, here's how the structure is, but we didn't do a whole lot with it. Now, we have to use that. Because without that, it looks like these two are the same when we put them on paper. So we have to find a way to express that 3-dimensional structure. So let's do this. I'm going to keep them in, just so we're all the same here. Let's keep the one stick that doesn't have anything on it, let's keep that one up. And we'll draw them as mirror images like this. So I'm going to put the C in the middle for carbon. The nothing is going up. The little ball is going out. And then I've got the blue one going out front and the red one going kind of in the back. And to make sure that we know which one's which, rather than just drawing those straight lines, we're going to draw a wedged bond for the one that's coming out and a dashed bond for the one that's going back. So that's one. And then the other one is right next to it as a mirror image. Something like that. So the terms that we use for these are either stereoisomers, which means that they're connected the same, they have the same connectivity, but they are not superimposable. So regular isomers or structural isomers have the same formula but are connected in different ways. Stereoisomers have the same formula and the same connectivity, the same connections, but they're still different because they're not superimposable. Their 3-dimensional shape is different even though everything is connected in the same way. And then the other term that we use for these enantiomers are exact mirror images that are not superimposable. And now I'm thinking maybe it's IBLE. Who's a good speller? Is it ABLE or IBLE for superimposable? We should look it up. Yeah, that's right. I mean, who knows? But the internet maybe is also wrong, but I'm good with that. Okay. All right, so when you see the mirror image like that, it's a little tricky because it really makes those two look exactly the same. Like when I first put these together and I held them up and asked you if they were superimposable, pretty much everybody said, well, yeah, they look the same. So when you do it like that, it really looks the same. So it's often more useful to put them like this, where they're more like in the same orientation, and we can more clearly see the differences. So let's do that. Let's rotate. Let's take this one and rotate it around by 180 degrees. So we'd still have our carbon here. We'd still have our empty stick going up. But now the circle is over on this side. The R flips out to the front because we're 180 degrees, so back goes to front. And the B that was on the front goes to the back. The same colors there. So now if we compare this one and this one, it's clearer that those are not the same because the front and back positions are switched. The R is in front on one of them, and the B is in back, and then the other one is switched. The R is in back, and the B is in front. Okay. Molecules that have enantiomers are called chiral. It's actually not just molecules, but we're gonna narrow it down to just molecules. So any shape really, or anything that has this property of its mirror image is not the same, it's not superimposable, is called chiral. And you can think of various ways to look for that. So if you think about your own body, if you think about your whole body with its bilateral symmetry, is not chiral. Because your mirror image, you look around, it would be the same as you. But your hands are chiral, because your right hand, your left hand, they're mirror images, assuming they're the same, but you can't superimpose them. You try to put one on top of the other, and it's like backwards compared to the other. So that's like what we did with the molecules. So molecules that are chiral are chiral have this mirror image that's not the same as itself. And so it's a way of looking at asymmetry. Things that are less symmetric are more likely to be chiral. Things that have a particular direction or a particular orientation are usually chiral. Things that are more symmetric are usually not chiral or achiral. So why do we talk about all this stuff? Well, sugars and amino acids in particular, of all the molecules we're looking at, for those, this chirality is really important. So let's apply this now and look at some sugar molecules. Carbohydrates are so named because they have a particular formula. They're built of building blocks kind of like this. And it's not exact, but when these were first being discovered, they noticed that if they heated it enough to decompose off the water, you were left with a certain amount of carbon, and they could do the mass ratios and figure out the formula there. So literally carbon and hydrate, or water. So the most common sugar, one that we're going to look at more in a little bit, is C6H12O6, which is glucose, and a bunch of other ones, as it turns out. And we could rewrite that as C6H2O6. So it's like a 1-to-1 with carbon and water. So carbohydrate structures, we're going to see a bunch of different ones, but we'll start with the more common, simpler ones, and then we'll work to some of the other ones. The simplest sugar is called glyceraldehyde. And its structure looks something like this. It has 3 carbons. With an OH on each carbon. On each of the 2 carbons here. And then the last carbon is an aldehyde. And most sugars have that type of structure. So let's build that with our models. Combine the models now. And let's say, what do I do with my models? Oh, thanks. So use whatever colors you want. Let's leave the hydrogens off for now. So only put in the carbons, the black ones, and then use whatever color you want for the oxygens or the OHs. So you'll need 3 of the black ones to make the chain of the 3. Then the double bond to the oxygen, the 1 oxygen we use with the curved bonds. So you should have something like that on one end. And then you're going to put the other 2 on the other ones. Now I don't have any more of the red ones, so I'm just going to use the blue ones for my other oxygens. Yeah. So carbon, carbon, carbon. Okay, no bond to oxygen, and then OH and OH. And we're leaving the other hydrogen. We're leaving the hydrogens off for now, just to make it easier to build. If you want to put the hydrogens on, you can. If you want to put empty sticks or whatever, that's fine too. But something like that. I only used the different colors because I didn't have enough of one color piece. Use whatever ones you want. Yeah, I mean, if one of you uses blue and one uses green, that's fine. or if you want to mix green and blue, just have something other than black for the ones that are coming off of it.
Wait, which one are we leaving out again?
Hydrogen.
Oh, okay.
Okay, so you have that belt. Is it pair up with another group or with the person next to you if you each made separate ones, and see if your two models are superimposable or not. So can you line them up so that every one is exactly the same or not? Oh, wait, no, do that. Well, here, let's see. The other and see. They have longer bonds. Yeah, it's right. Okay. Good. So if you found them to be superimposable, that's fine. Take one of them. Take one of the two. Take the middle carbon and just switch where the blue one is connected, or the red one, or whatever you used was connected, from whatever hole it was in to the other one on that exact same carbon. So you're just moving it one hole on the same carbon. And check again if it's superimposable.
And the one that was connected to the middle?
Yeah. The one that was connected to the middle one. Check again if it's superimposable. Don't move both of them, just move one. Just one of the two options. Now check it again. Alright, so check it again. Okay, so now are they still superimposable? Let's see. Now, no matter what you do, you can't get them all to line up this way. Okay, see that? You're gonna borrow these with me? All right, so if you switch one of them, so here's two models that look pretty much the same, right? But if we try to actually superimpose them, that is, put them so that each atom lines up exactly with another one, you'll see that it doesn't work. Yeah? And another way of saying that is that the mirror images, if you make these into two mirror images, which they are right here, mirror images, but they are not superimposable. So that makes them stereoisomers or enantiomers. That also makes them chiral. And that means that we have to be more careful than what we just drew there, because that structure is too general. It doesn't take this into account, that we could have two different possible structures that are actually not the same. So we have to draw this in a way that does make them look different. It makes it obvious that they're different. And so we're going to try that now. We're going to look at two different ways of drawing this. One is, I think, better reflective of the actual structure, and the other one is more of a convention. So let's first just look at the regular line structure of this. So we would take our 3 carbons like that. And then we'd have our aldehyde going off this way. And then on each of those carbons is, or on that middle, I'm sorry, on the N carbon there is an OH. I'm going to write it as HO just because that's how it would be connected, but same thing. So it's actually that middle carbon that ends up changing. Remember, that's the one that we switched to make them non-superimposable. So that means we're going to put that dash and wedge notation. And one of the enantiomers, one of the isomers is going to look like that. And the other one has them switched. And those are not the same structure. Those are enantiomers. All right. So with sugars, this becomes really important because what we're going to see next is that we make the chains bigger and bigger and bigger as we develop different types of sugars. And as the chains get bigger, the number of these carbons that we can flip actually increases. And so we have to keep track of all of them. So sometimes these line structures aren't the best way to do it. The convention is to use something called a Fischer projection. And it's a little bit tricky, but I think we can do it. So let's take this structure. I'm going to leave it there. Move another one over here. I'm going to give myself a little more room. Okay. Now here's where the little bit of weird brain stuff comes in. Let's imagine that we are looking at it from the top. So that's an I. So everybody build that specific one. So that means take whichever one you had. You're going to take your 3 carbons, make sure that your double bond to oxygen is on the right. And if everything is that way, the O in the middle should be coming out at you. Not going back, coming out at you. Yep, that one looks good. So you've made that exact structure with the OH coming out toward you. If you're looking at it, that colored one or that different one is coming straight out toward you. Give you a minute to get that. You get it? You got that? Where's your double bond?
I was like, yeah. So we cancel it, guys?
Yeah, use 2 of the third ones. Is that way you're sure that it's going to go right? Anybody else having trouble getting in the right position?
So the one that are going off.
Yes, the ones coming off is the main black. Yes, that's right. No, you got it. Yeah, that's right. So the double bond is going off to the right. So it's like out of you, but look at the orientation of the chain. It should be the middle one should be up. So you got that shape chain. You got the OH coming off there. Double bond oxygen coming off over here. This is wrong, so that's got to go. Yeah, that was good. Because you got it upside down. So the chain, if you imagine the regular chain, it kind of goes up like that. So that's like that. So if we put it that way, This is in the wrong spot. So we're going to put this side. So now you see how that's the same as that? The same thing. This is all very subtle, and especially when you are first seeing it, it can be difficult, but we have to make sure that everything is exactly in the same place as how we drew it up there for this to work. You got it? You got the, so you want this little oxygen. All right. Anybody else, any other questions? That's good. No, that's flipped. Look at that little chain. This way. So you have to make a double wheeling. So that's just the opposite. All right. So now we've got this. So now I want you to look at that picture, that diagram with the eye on the top. And we want to look at it from straight down onto the top one. So orient it kind of like this so that you're looking at that view. Everybody see that? If you do that, it should look something like this. So you should have a carbon in the middle that's kind of like pointing toward you almost. Then the O from that one is coming off to the right. Then there's another carbon below it. And then another one on top that has the double bond O on it. Something like that. The key is that that middle oxygen should be pointing to the right when you're looking at it with the aldehyde on the top. So if the carbonyl or the aldehyde is on top, the oxygen on the middle carbon should be pointing to the right. Does everybody have that on theirs? You see it? Pointing to the right? Okay, let's fill in the rest of the picture, which is the hydrogens that we've left out. So this O is actually an OH. This carbon on the bottom actually has two hydrogens and an OH connected to it. And then on the top, this also has an H. It doesn't matter which direction it's coming off of for that one because it's a double bond. And then there's actually another H that we haven't shown coming off to the left. You should see an open hole on that middle carbon going off to the left. You see that? So this is called a Fischer projection. And even though it was confusing to get to that, it makes it easy to see the orientation of a particular stereoisomer of the sugar. So let's look at some of the features of the Fischer projection. So you have the aldehyde on top. And this is going to be true for any of these types of sugars. We're going to look at other types of sugars that have ketones later, but for these types of sugars, the aldehydes are on top. There's always CH2OH on the bottom. And then the orientation of this one that I circled determines something that we're going to call D and L. So sugars exist in two orientations, D and L. Those letters come from this experiment that you can do to actually see this experimentally, where you do a thing with light, plain polarized light, and it rotates the light either to the right or to the left. And because of the words for that, that's where the D and the L come from. Not really important. But it is important that there's two different types of sugars. So let me redraw this down where I have a little bit more room. The one that we just drew again is going to look like this. I'm going to now abbreviate the aldehyde as CHO because we learned that's an abbreviation for an aldehyde. And I'm going to put the OH over to the right and the H over to the left. And so because that OH is on the right in this particular type of projection, we're going to call this D-glyceraldehyde. And that means that it's an enantiomer, it's opposite, it's mirror image. Where we flip that H and OH is L-glyceraldehyde. So the position of that OH in the Fischer projection is what determines whether we have D or L sugars. And D or L sugars, even though when we draw them and when we build them, it looks like a super subtle difference to our body and to other living things, it's a totally huge difference. Almost all naturally existing sugars are, man, I think it's L, but I totally just lost it from my brain. Yes. Man, why can't I? I can't remember which one is more important, but we'll get to it and I'll look it up. But for some reason it just went out of my brain. Let's look at the Fischer projection again. So we take our molecule and we look at it from the top, from where the H's and OH's are kind of pointing out at us. Like this. And in that particular projection, instead of talking about dashes and wedges, things coming out at you or things coming back, we're just talking about right or left. So things being on the right side of the chain or the left side of the chain, that's what determines the stereochemistry. So for instance, when you built them and I was asking you to switch them, the thing that made the biggest change, the biggest switch, was, or the only change, was when we took this middle one and we switched it from one side to the other. And when you're looking at it like this, you can see how that moves it from the left side, or the, I guess to you it's the right side, or the left side. And that's what changes all of that stereochemistry, that change. So we use Fischer projections because it makes it easy to see if something is on the right side or the left side, and how that changes whatever sugar you have. Okay. All right, so let's look at what we got when we build these up a little bit and get some bigger sugars. So let's look at some biologically important sugars. D, right? I'm getting it mixed up with amino acids. I think that's why. So the D sugars are the common ones. The L sugars don't generally exist naturally. I believe that's true. That's what Google said? All right, awesome. We'll go with Google. That sounds right. Because the amino acids, it's the opposite. The L amino acids are the common ones. The D sugars are the common ones.
We should write
they're both glyceraldehyde, but one is D-glyceraldehyde and one is L, and those are different molecules. Those are stereoisomers or enantiomers. And that's why we spent so much time with the models and looking at it this way. Because if I just drew those two structures and we didn't know that we were looking at this particular type of projection, you would say, well, of course, those are the same. So it's important that we know now when we're talking about these things, they are not the same. The good news is we're never going to use these outside of this context. Fischer projections are used to look at sugars and to look at amino acids. So there isn't just going to be some random molecule that you have to be able to put into a Fischer projection. They're always going to follow this nice pattern. But it can still be a little confusing if you don't know what you're looking for. So let's look at some bigger sugars now and how we use the Fischer projections to tell them apart. Oh, yeah, sure. Sorry. I was just plowing through. I thought it was just too exciting for everybody. But no, let's take a break. It's definitely, we've been working for a while. Have some more candy. Take a bathroom break. Maybe come back in about 15 minutes. But I don't know. I just grabbed stuff from my kids' Halloween things. Okay, so here's our small sugars, our glyceraldehyde. So now we're going to build it up. There's a whole bunch of sugars now that like you can add one more carbon and then another carbon, another carbon. We're going to skip over most of that. We're going to look at the most important ones, which probably the most important sugar is glucose. So if this is glyceraldehyde, let's look at a Fischer projection for glucose. We're going to take one more abbreviation with our Fischer projection just because it's bigger. And instead of drawing each individual carbon along the chain, we're going to just make crosses, and the carbons will be in there. So I'll write that. But glucose has a similar structure to glyceraldehyde in that it still has an aldehyde on the top and this CH2OH on the bottom. But instead of just one carbon in the middle, there are 4 more carbons. So it's a 6-carbon sugar instead of a 4-carbon sugar. So we're going to draw those 6 carbons like this. Each intersection with the middle there is a carbon. And each carbon has an H and an OH on it, just like the 1 carbon in the middle of glyceraldehyde. For glucose, the order goes like this. H, OH, OH, H, H, OH. And then just like with glyceraldehyde, this bottom carbon determines whether it's D or L glucose. So D and L glucose are actually not exact mirror images in this way. They look like this. So same bottom, same top. Mostly oops, no, we got it switched. They got to be our mirror images, right? It's actually not in here. That's okay. So if we make the mirror image of D-glucose, we've got L-glucose. And you can see with the D1, the OH is on the left, and the L, the OH is on the right. Or, I'm sorry, the D, the OH is on the right, and the L, the OH is on the left. So there isn't, I was looking through, there isn't a great figure in the book, and I don't want to go through it all because you don't have to know all this, but I want to show you a picture of all the different possible sugars that you can get with 6 carbons. So we've got glucose. These are just the D sugars. We've got glucose, which we just drew right there. All these other sugars here are different. They're different sugars. They have different names. They interact differently. They have different sweetnesses. They're metabolized by your body differently. But the structures are all very, very similar. What are the only differences? What differences do you see among those 8? How? Yeah, the orientations of the H and OH. So these are all stereoisomers of each other, which make completely different sugars. They're all connected the same way. They're all 6 carbons in a chain with an aldehyde on one end and an OH on each carbon. But depending on the orientation of the OH, whether it's coming out of you or going back, or in the Fischer projection left or right, completely changes what we call that sugar and how it interacts with the rest of the world. So that's why this idea of 3-dimensional orientation is so important when it comes to these types of structures, because you totally change the type of sugar that you're talking about based on which orientation the OHs are in. All right. Oh, also notice on this one, the bottom one of these carbons the one closest to the CH2OH, is always on the right, and that's because these are all D sugars. If it were on the left, they would all be L sugars. So the opposites of all of these have the same name, but with L instead of D. We make a mirror image, which means we switch all of the H's and OH's. We would have the L instead of D. You don't have to memorize all these structures. Okay. Just the bottom one. Just this one right here. Yeah. If that's on the left, it's L. If it's on the right, it's D. Okay. So we just spent all this time working on this, and now I'm going to tell you it doesn't quite work that way. Sugars don't hang around in these long chains like that. They actually make more stable. They do exist like this sometimes transiently, but they generally make a more stable structure. All right, and this is called it's called mutarotation, but that word isn't even in here, so we're not going to mess with it. So let's take glucose and look at what happens to it. We'll draw glucose again. You'll be good at this by. And this time I'm going to draw the whole aldehyde out because it actually we're going to do something with it instead of just drawing CHO. Okay, so we've got H, OH, OH, H, H, OH, and H, OH. There's our D-glucose, right? Okay. So let's see if I have enough carbons to do this. Yep, so I need 3 more carbons. If you want to follow along, I'm making a model of this. You can do that too. Maybe you could, if you have 2 of them around, you can combine the 2. So I'm going to put 6 carbons in a row. Six carbons because we got the top one and the bottom one too. And now if you want to get them all oriented properly, whoops, I'm locking down one here. Remember how in glyceraldehyde we said we were going to look straight down like this? Well, for a bigger one like that, we have to kind of curl it up to get it to work. And then kind of follow it around with the curl. It's not going to want to do it really in the model. It's going to kind of like try to collapse on itself, but that's how you do it. So we got the aldehyde up here. The next one's on the left. And then as you kind of follow it around, it goes to the right. Then the next one down is going to be, or I'm sorry, that's your left. Sorry. So we go right, left, right, and then right. And make sure that the next one is always kind of going behind. So it's sort of all curled up. And then the very bottom one, it doesn't matter where you put that one. Okay, it's just enough to think. All right. Don't worry if you can't quite get it. If you stretch it all out, look kind of like that. So you have coming out of you, coming out of you, coming out of you, and then going back. Don't worry about it if you don't get exactly right. I'll do it. But I'm going to make that no. All right. So here's what happens. The the OH near the bottom, the one that we've been using to tell D and L apart, this one here, actually reaches around and connects to the carbon of the aldehyde. And that turns the aldehyde into an alcohol.
That doesn't never happen.
Wrong number, I guess. So you don't have to necessarily do this, but if you got it, fine. This will actually work with any orientation that you put your things in. So the second one from the bottom of the chain, we're going to put a bond in there. We're going to reach around, and it should actually work pretty nicely. And it connects right up to that carbon that has the aldehyde on it. It actually makes a pretty nice ring. It's not strained. You don't have to like stretch it to get it to connect. And that's actually why it does it. It allows it to preserve its bond angles and be in a little bit more of a stable state. So it makes this ring structure like this. And one thing that you notice when that happens, this would actually become an OH, but we'll kind of like that. When that happens, these other OHs that we had on the chain, they're fixed in either up or down positions. So just like on the chain, they were left or right, or coming out of you, or going back, whatever. When we do this thing and make this ring structure, they're stuck in either up or down positions. And so just like how in the Fischer projection, we have the left or right for the OHs, in this ring, we have the up or down. So when we draw glucose, we draw it like this. We draw that 6-membered ring with the O in it. The O is actually a part of the ring, see? It's actually a part of it. And then we look at where the OHs and the H's are in terms of being up or down. So at each carbon, there's going to be an up position and a down position, even though it's not perfectly flat like this. So let's try to make sense of this. To track this around and be able to make these things, we need to know which carbon is which. So let's number our carbon starting from the top. So this carbon that has the aldehyde on it is number 1. Then we've got 2, 3, 4, 5, and 6. In this ring structure, which is called a Haworth projection. We had Fischer projections, now we have Haworth projections. Carbon number 1 is right here, followed by 2, 3, 4, 5, and then 6 is this one up there. And we can actually figure out where the OHs are going to go on carbons 2 through 5. If the OH is on the right on this projection, like on number 2, over here the OH is going to end up down. If the OH is on the left, like number 3, the OH ends up. So let's see how that works. Number 2, the OH is on the right, so it ends up down. Number 3, the OH is on the left, so it ends up. Number 4, the OH is on the right, so it ends up down. Number 5, the OH is on the right, but that's the one that connects and is in the ring. So that's the O from that particular OH. And then on number 1, that's where the aldehyde was. So that actually can go either way. There's 2 different possibilities, one where the O is down and one where the OH is up. So when we look at structures of sugars, especially when we look at larger sugars, we're usually going to be using this ring notation instead of the straight line notation. The straight line makes it easier, the Fischer projection makes it easier to tell one sugar from another, but in reality, these sugars usually spend more time in their ring form. That's what we see over there. All right, so using that example, see if you can do one. Let's grab one of our sugars over here. Let's say galactose. Try to get both of these things on the screen at the same time so you can see it. So take D-galactose and see if you can draw it in that projection the same way that we did with the glucose. Remember that we're really doing the same thing, but the OHs are going to be in a little bit different place in the galactose. Go ahead, try it. If you drew it, look around with people around you and see how yours compare. If you're still working on it, that's fine. You're working on it.
Yeah, we thought I had half it, but how did we get this one over here?
Yes, that's the station. That's so you've got the CH2OH there, right?
So here, this one.
Yeah.
This line goes here.
Good.
This line goes here. This one goes here. So it looks the same.
No, not quite. So this carbon right there. This carbon. So think about what's connected to that one.
So this is.
You get this connected to it. You get the H connected to it. You get the O connected to that. So that's what makes the connection. So this OH is actually like that.
So this always comes from the bottom right here.
Actually, this first one can go either way. The first one will go now. Go either way.
So this is the,
So that's that, right?
so.
Yeah.
For the test, are there any of these we have to like memorize? Like, would you give us the test like draw glucose, but you wouldn't give us the original structure?
You don't have to memorize the structures.
So I don't have to do this on the test.
You have to do this, but you don't have to memorize the structures.
I need to see you do this just like that.
Okay. Before I say that for sure, let me check the objectives. Yeah. All right. So for this one, we're going to make that same form. So we start with that 6-membered ring. Okay. And it's always helpful to number things. So you got 1, 2, 3, 4, 5, and 6. And those carbons are 1, 2, 3, 4, 5, and then 6 is connected up from 5 here. So let's put in our lines. The CH2OH is always in the back right there on the top. And then if we go back to carbon number 1 started as an aldehyde, so there's no direction as to whether it's going to be up, the OH is going to end up being up or down. Both are made, they have different names. You'll see it if you look through the book, alpha and beta, but we can just say it doesn't matter. So we put the OH there and the H there, or you could put the OH on the bottom, same thing. Where it does matter is 2 through 4. Number 2, the OH in the Fischer projection is on the right, so that means it goes down on the Haworth projection. On number 3, the OH is on the left, which makes it go up. Number 4, the OH is on the left, which also makes it go up. And so that should be your structure. And if we compare that to glucose, again, it looks very similar. As you would expect, glucose and galactose only differ at this carbon number 4. So this one has the OH on the right, this one has the OH on the left. So similarly, their ring structures only differ by right there.
So for number 5, is
Yeah.
label number 6, where
Number 6 is this carbon right here.
then how would the OH for number 5, the OH
This one?
yeah, where's that OH go?
So that O is no longer an OH. It's this O that's part of the ring. Because we make the connection by connecting that O to that C, to C number 1.
Okay.
Yeah. All right.
Wait,
Yep.
So when do we know when it matters for the first one if the OH is at the bottom or at the top?
It never does for that first
Oh, it
one.
never did.
Yeah.
Oh, okay. Oh. Okay.
So you can never be wrong on that first one. There are different names for each of them, but we're not going to go through why I like remembering those. So it can be either way on that first one. Yep. All right, so I want to show you another common sugar, fructose, because it's an important biological sugar. Access is denied. Let's try again. I don't want to draw it this time because I don't want to get you confused with all the other stuff because it's a little bit different.
Whoops. But I do want to show you it, so I have to get to McGraw-Hill thing. Get the book. Okay, try that again here. This is page 579. All right. So this is what fructose looks like. I'll put it in the notes also. So one thing that makes fructose so different, there's a few other sugars like it, but so different from all the other stuff we've been talking about, is that instead of an aldehyde, it has a ketone. That carbon double bond oxygen, rather than being at the very end of the chain, is like one away from the end of the chain. So glyceraldehyde and glucose and galactose and those other sugars we looked at are all called aldoses. And fructose is a ketose. That suffix OSE has to do with sugar. So anytime somebody says something about ose, it has to do with carbohydrates or sugar. So a ketose is a sugar that has a ketone, and an aldose is a sugar that has an aldehyde. Because fructose's carbonyl is a little bit farther down the chain, so instead of carbon 1, it's carbon 2, when it does this rotation thing, when it does this ring formation, instead of a 6-membered ring, it forms a 5-membered ring. And so you can see in that diagram, again, it can go both ways with that number, with what's now number 2, carbon number 2. And then the other ones are dictated by the same rules. We're not going to worry about these, but I wanted to show you that because fructose is, of course, an important sugar that is part of, we get from fruits. But it also comes up in our next part, which we're going to talk about disaccharides and polysaccharides. What do you think this means? Any ideas? Disaccharides and polysaccharides. 2 sugars or many sugars. Yeah, 2 sugars or many sugars. So those molecules that we've been looking at so far, all of these are monosaccharides, single sugars, sometimes called simple sugars. And these structures are now a little bit larger, and these are molecules that are made from hooking other sugars together. So let's look at how that works. These are 2 or more sugars. So these are starting to get a little bit big, so I'm going to copy the pictures in from the book and not draw them. You don't have to draw them. Remember, these notes are always available to you. So that's what we're going to do here. For these next several chapters, really, we're going to be relying more and more on pictures because of just the size of the stuff that we're talking about. Why can't I see what I need to see here? Oh, here they are. Okay. So there's our fructose. Okay, I guess we need the next section. Okay. So here's what it looks like. Where's our picture? All right, let's look at lactose. So does anybody know what lactose is? It's in milk. It's the milk sugar that we just did, right? So everybody knows what it is because we just did it. I don't know. Maybe you forgot. It's okay. It's late. But yes, that's milk sugar. It's an important biological sugar. A lot of people can't process it. In fact, most adults can't process lactose to some degree or another, which is why if you drink enough milk, you will have some problems. It doesn't matter who you are. But if you're lactose intolerant, it means you can't even tolerate a small amount of lactose. Yeah, is that fun for you? Yeah. So lactose is a disaccharide formed from the linkage of glucose and galactose. So here's glucose in its ring form. Here's galactose. Those are the ones that we just did. And those two molecules side by side, they actually kind of flipped around on us here. So we need to spin one of those around, or we need to kind of pull this up a little bit. The OH from here and the H from here disappear and form water. So that's called a dehydration reaction because you're losing water. And in their place, the oxygen then bridges the two rings. So you can see that right here, that the oxygen bridges the rings, and that's called a glycosidic bond or a glycoside linkage. Have you heard that term glycoside? That's what it's talking about. It's the way that two sugars can connect together through that type of bond, through that oxygen. And that's what lactose is. So lactose is a glycosidic linkage of a galactose and a glucose molecule. And in doing that, then it makes a totally different sugar. So people who can't process that don't have the enzyme lactase that breaks that apart. And people who can process that, specifically most young children, do have that enzyme and that can break that particular sugar down. This language here, I'm going to copy this over so we have it in our notes, just for those of you who don't have this.
Wait, lactose is like glycosidic mixture of glucose and lactose?
Glycosidic, yeah. Bond. Okay. That's that link there. And that language for that, or that label for the link, the beta 1 to 4. The beta part has to do with whether that one OH that I said doesn't matter is up or down. The 1 to 4 part is important because we're going to use that to compare this to some other links too. It means that carbon 1 on one of the rings is connected through that oxygen to carbon 4 on the other ring. So that's the 1 to 4 linkage. And that puts that in a particular geometry and in a particular orientation, and that makes lactose what it is. If those were linked in another way, we'd have a totally different sugar. Sure. You know that it's on Blackboard, right? That's fine. Yep. All right, so let's look at another biologically important disaccharide. So you can see this linkage is very different. I'm just going to copy it over because it's easier to see over here. But now we have, again, a glucose molecule right here. But this time we're going to link it with a fructose molecule, and we're going to link it 1 to 2 instead of 1 to 4. So it's almost like one of these is kind of on top of the other one. Linking those together makes sucrose, which is more commonly known as table sugar. So this is the regular old white sugar that you get from refining particular fruits, particularly sugar cane or sugar beets or sometimes corn. And that's how we get sucrose. Sucrose is made of 1 molecule of glucose and 1 molecule of fructose. So it's technically half and half glucose and fructose. But it is, of course, linked together, so it's a different structure. So this is why, like a lot of people, well, it's not quite as much, you don't hear quite as much anymore, but for a long time, people were really worried about high fructose corn syrup. You heard of that? So high fructose corn syrup is about 55% fructose. So it's really not much higher in fructose than regular sucrose is. This is about 50-50. It's a little bit more. It's a lot higher than corn syrup is, which has very little fructose in it. So that's where the high comes from. But it's not much different from sucrose. So there actually isn't, there is evidence that fructose as a sweetener is worse for you than other things like sucrose, but there's not evidence that high fructose corn syrup acts particularly differently in your body from sucrose. But this is sucrose. It's a linkage of those two molecules. So now we have a 1 to 2 linkage instead of that 1 to 4 linkage. All right, get that a little bit? All right, let's look at the polysaccharides. And I'm definitely not going to draw these because they're getting pretty big. So with polysaccharides, instead of just 2 of these hooking together, you're talking about many, many, many molecules hooking together. Hundreds or thousands of these molecules hooking together to make what we call a polymer. The most important starches or polymers that we're going to talk about, polysaccharides, are starch, which there are different starches, but we're going to primarily look at amylose and amylopectin. And then cellulose is another one is a separate one that we'll look at in a minute. So let's look at amylose and amylopectin and the difference and where we can see that. All right. So here's amylose. Amylose is a 1 to 4 linkage of glucose molecules. So this is just glucose, no other sugars, linked together one after another, all connected through that 1 to 4 linkage, so kind of across the chain. Then because of all those OHs, the intermolecular forces, the hydrogen bonding, causes this to kind of curl up on itself a bit, and you make this ultimately makes this kind of helical structure.
Is that only for glucose? Is amylose like anything? So it's the same.
What do you mean?
So is amylose always going to be the one?
Yes, amylose is just one thing. It's just the one.
So it can be.
Nope, that would be a different molecule. So this is a major component of what we call starch. So when you talk about cornstarch or potato starch, when you look at rice, other kinds of foods like that, wheat, those types of starches are made of a lot of amylose. And then similar to amylose is amylopectin, which where is it? Okay, on the next page. So here. So whereas amylose is just those 1,4 links, amylopectin is a mixture of 1,4 links and 1,6 links, so going across the chain. So this makes it branched. Still just glucose. So this one A here is, or B right here, is kind of a like bigger view of what amylopectin might look like. So where amylose is more of a straight chain, amylopectin is more branched. And those starches are usually together in biological systems, and we all have enzymes that break those down called amylases. And that's why you hear like when you eat starch or when you eat like rice or potatoes, it's kind of like eating sugar, because those enzymes in our body do break these down into glucose. So that's why those things end up being glucose in our blood. That's literally what they're made from, and so they're broken down into those same things. We store our energy in something called glycogen. So when we eat sugar or we eat this stuff, it gets broken apart and then gets reconstructed to stored in something in a carbohydrate called glycogen, which is very similar to amylopectin, and then that is broken down when we need energy. So we compare these then. These are all things that we eat and that we use in our body, and we can compare these then to cellulose, which is also a 1-to-4 linkage of glucose. What is cellulose? Does anybody know? Like, what is it in? Plants. It is plants. It is plant cell walls. It is what plants are made out of. It is wood, right? Wood is made of cellulose. Stems are made of cellulose. All the structural parts of plants are made of cellulose. Can we digest cellulose? No. We cannot. We cannot. That's what we call fiber, right? You eat it, you don't digest it, it just pushes everything out on its way out. Who does eat cellulose? What kind of animals? Cows, yeah. You need those multiple stomachs, different kinds of enzymes and things like that to break down cellulose because it is so strong. Yeah.
Don't cows like pick up rocks and put it so much they don't break down?
Maybe, I don't know that much about cows. Yeah. Does anybody know? It seems reasonable. I mean, yeah, sure, why not?
Oh my god, Alex, you can Google it.
Yeah, Google it. Do cows have rocks in their stomachs to help them digest? I don't know. But this shows the chemistry of it down at the molecular level, that it is this 1,4 linkage of glucose. But it's not really a great view of what's really causing that difference. So let me see if I can find a good picture of it. Yeah, this is a better picture of it. So let's look at what's going on here. So this is more like the real three-dimensional structure of what cellulose would look like. You have these chains. So here's your glucose rings. There's the glycoside linkage. There's another glycoside linkage. You'll notice they're kind of switched, so they go back and forth, forward and backwards. So that's the chain. That's the main chain that we showed in the other picture right here. But what makes cellulose so strong is when it's in that orientation, it's having these hydrogen bonding interactions with all the other chains. So this one is a separate chain down here and a separate chain down here. But the hydrogen bonds are lined up just right. So you have all these really strong intermolecular forces among the chains. So that makes it very difficult to tear these chains apart because they're so tightly bound through the intermolecular forces. And that's why we don't digest cellulose. Why you need a lot of time, a lot of grinding, a lot of like mechanical energy to actually get these things to come apart. And so when we eat animals, we're essentially using them to digest the cellulose and turn it into glycogen and other sources of energy that we can then eat. All right, so that's cellulose. So we learned a lot of stuff about sugars and carbohydrates tonight. We're not going to stop because sugars are also the basis for a lot of other things. When we talk about DNA, DNA has a sugar backbone. So it has a bunch of sugars lined up with some other helper molecules there. When we look at things like pharmaceuticals, there's many classes of drugs that are based on sugar structures. Aminoglycosides are one, which is a type of antibiotic. So, so these sugar structures are so important to life that we see them coming up again and again in different forms. So we'll see them again when we talk about DNA. We'll see them again when we talk about metabolism when we get that far. But this gives you a basis to what those specific structures are. All right, seem okay? I know that's tough.
Are we done for the night?
I think we're done for the night. Any questions? So we will do another quiz on functional groups on Wednesday. So be ready for that, as well as the lab on soap making.